I have to record your presentation because you don't have the screen. The screen recording software.
Ah, okay.
So I have to kind of cut and paste this.
Okay. So now you finished?
Yeah.
Oh, okay. So in the last meetup in the pub, I discussed with some of you my problem that I had a research paper what was dropped back and dealt with audio data, and the main review stuff was that why didn't you evaluate your stuff with deep learning? So I had to start to work with deep learning, and I'm mainly working in C++. So I looked about, okay, let's check the C++ libraries or whatever available frameworks for deep learning, not only just checking my data with deep learning, but later on maybe reusing my software or developing models for my software if it's really so good. So as last time I mentioned, some TUT researchers who work with sound event recognition, they had some experience with deep learning in that field, and they had mixed results. So sometimes deep learning was better than traditional stuff, sometimes it wasn't so good, but so there are no too much experience in this field also to apply these techniques. So I started to look into the alternatives, and from bad to good, there is the mxnet called library, which has GPU acceleration, but you have to very in details put together the network, not like so easily like in TensorFlow. So it wasn't a good alternative even just to try it, because it looked very ugly and they didn't have too much documentation also. The next one is dlib, which has quite many examples, and they implemented previous year the deep learning API. It has GPU acceleration and many examples, and everything is just so nice. It's really accelerating the training and blah blah blah. It has also the deep learning hell over this MNIST dataset implementation, like training, but the API is so sucks that it's just not usable, because I don't know if you work with C++, but the guy exposed the network architecture as template parameters just because he had to serialize the data, so saving the network weights and this kind of stuff and loading back, so providing this kind of API, and he decided to add the network architecture into template parameters. What it means that I have to hard code the deep network architecture or model or topology in compile time, and after that I can't modify it. I have to recompile my code, which is very bad, because normally I'm doing like also parameter search, or in this case I also started to check like topology search for different neural networks, and therefore in the runtime I have to drop together the stuff. So unfortunately dlib is completely sucks because of this. And I think the previous meetup, Caffe was also told me that, oh, this is good and I should check it. And also on the internet, I've seen all around like, okay, Caffe, C++, blah, blah, blah. And I had a really bad experience about it. I tried also the original Caffe implementation, which comes from BVLC or whatever department. And if you check on GitHub, they have like 800 bugs or issues and 300 pull requests. They are completely out of sync in development, which is a very big warning sign. And the Caffe Intel is good from that point of view that Intel forked the Caffe and they started to work with a bigger team on that, so they are not really behind. But I think the implementation is quite differs already because they put really quite a lot of efforts to make the Caffe framework work very much optimized on Intel. So they integrated their computational doing everything quickly in SSE and blah 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 libraries, and also a quite big limitation of the Caffe by default that it can work or train just in a single thread on CPU. So you can't, if you have a 16 core server rack somewhere, you can't train on 16 core your network because it just doesn't scale up. It's really designed for GPU, but the Intel fork, they made it work to expose as many cores as it can, depending on the network topology and the error propagation. And the problem is that it's mainly like Python, and it's written in C++, but it's not really exposed too well in Python, and it was a pain in the ass to put together really even just the network model description, because they are using called protobuf files to, so the network topology is described in a text file, in a JSON-like text file, which is parsed by the framework, and then it builds in the memory the network architecture, and it has, I think, pre-built functions to load images from the disk. So you are just specifying what to load, and it loads and feeds the network strings and blah blah blah. And you also, they are calling it solvers, which is especially a config file where you can specify what kind of gradient function or different kind of training parameters. So all kinds of training parameters you can specify in a solver file. So basically the training and testing is specified in text files. So it's not really in source code, although you can write it also in source code, but it's not designed for that. It has really a bad documentation, and they are changing also the API. Finally, I was able to use it, but it was really hard. The other is the called Dynet, or Dynet, I don't know how to call this. The Dynet is written by a research group somewhere, and you can see it also like this is written by research guys, not people who actually designing API for common usage. How it differs from the other frameworks, that in Dynet they focused on to have a very generic framework, and they from the beginning they think about like a graph representation of the neural network, which means that there are, for example, in the previous slide and in my slides I will talk about convolutional neural networks. They don't have, for example, convenience class just to drop together with a few lines of code a convolutional network, but they have a wired graph-based definition, like how to put together. Maybe I would say that the graph nodes or the graphs is like a tensor concept in the other frameworks. It's similar to that, but it's not so easy to put together, but it has GPU acceleration, and it has some examples, so I could really work with that, and but it also failed out. I will detail it later on. And my favorite one currently, where I'm also starting to contribute fixes, is the tiny-dnn. It's formerly called tiny-CNN, after like tiny convolutional neural networks. It's a header-only C++ library. That means that you just compiling your neural network when you're compiling your C++ code. So there is no library what you have to be provided for Android or something, you are just grabbing the include files and you can just immediately start to implement. As I could see, it's a quite popular thing because they don't have GPU acceleration, but from the beginning they have optimized backend for SSE, AVX, and this kind of instruction sets, and also it scales up to multi-cores. So they are calling it in the tutorial or introduction, but it really scales very well on multi-core CPUs, and I will tell you why this is a really cool library in the later slides. And one shortcoming of this framework that it doesn't have GPU support, although the guys are working on that, and it's mainly like providing means to put together the traditional multi-layer perceptron convolutional neural network types. So there is no, and like they have like batch normalization layer and this kind of common things, but there are many different kind of neural networks are currently, and topologies are in the field, like these recurrent neural networks, which were also proposed to me. So it's not good for everything, but currently for me it's quite good. They have a big user base and their stuff is, it's a very clean code, very good. They don't have memory corruptions or this kind of stuff. It's really very good and clean code, very well documented what is already written there, and they have examples, and they have many different kind of user base, so like on Android, iOS, and many different platforms. This can be just compiled and used, so it's really cross-platform. It's good for embedded devices or any other. Just really shortly, so it's just so easy to put together neural network in this with this library. So they also have support to put this kind of graph-based neural networks, but I so far just use this called sequential. Sequential means that you are just stacking layers from the input until the output on each other, and that's it. And this is like just from their examples. So this neural network gets an 32x32 input, and they have in the first layer like convolutional layer, and after that the usual pooling layer, which is an average pool here, and after that there is two fully connected layers. Inside the template parameters, they are telling the activation function like tangent hyperbolicus here and this identity here, what I never heard before, but especially it's kind of softmax like function, and they have the usual kind of optimizers like this Adagrad, but they have Adamgrad and I don't know, whatever. But I just started to use the default parameters everywhere, and I got good results, so I didn't have to play too much with the different kind of optimizers, and like the error function is this mean square error stuff. I didn't have to bother with this. It just worked. So my data is audio, as I mentioned. I have 14 sound events in my paper, what I wanted to recognize, and I'm generating 48 features for the feature vector, and one part, the majority of the features are coming from the MFCC components, which is like you have the audio signal, you are dropping a Fourier transform, and after that you are summing up the components with some other operations, and you are getting some numbers which mimic the human hearing. in this case, and they are like the standard features for audio for many years because it's just it's very powerful. And I have just some audio statistics, so I'm just calculating some mean, standard deviations, and blah 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 on the audio signal. Doesn't matter. Yeah, what I wanted to tell here that I'm not doing feature extraction in the neural network, so I know that this is yeah, using autoencoders, extracting the features, yeah, it will do magic and blah blah blah. In this framework, I think, for example, there is no autoencoder support, and honestly, I don't care currently. I just wanted to have something quickly to compare with traditional methods. And in the field, what I just read, like papers from previous year or in the last 2 years, they are doing the same. So they are not extracting the features and using it for recognition. They are also just using some pre-built features, and they are using the neural network based upon that. And I'm using aggregation. This gives some kind of temporal meaning for the feature vectors. It means that I have the feature vectors in every 120 millisecond audio window, which are coming after the other, and I'm getting 9, and I'm calculating mean and standard deviation for these 9 vectors for the first feature, for the second feature, third feature, and blah blah blah. And I will have 2 numbers for every feature, one mean and one stdef. And because this is like for 120 milliseconds, it will generalize a bit better, and it will have some kind of temporal meaning because I'm not using a temporal neural network or whatever. It's static. I'm just showing it static frames. It doesn't know what is after that and before that. I'm just learning individual feature vectors. Feature scaling. I could see that the best thing to feed the neural network, at least in this framework what I'm using, and in the other frameworks it was also the case that the features are scaled between 0 and 1. You can do it between -1 and 1. I could see this on the internet, but usually it's called rescaling for the feature pre-processing. I'm using just that, so every features are rescaled between 0 and 1. And for the problem, and also in the paper, I have different kind of data sets. So there is simple, medium sized, and there is the biggest one, which is the most difficult to learn. And these are I just put it up the numbers that this is the biggest one, which has almost 20,000 feature vectors to learn, and I'm evaluating on 800,000. So it's not big data, but it's more than just a few examples. And I'm using convolutional neural net implementation. How I came up with this, I'm very lazy. I've written an application which is just drops together randomly different kind of layers with different parameters, maximum 9, and it starts to calculate, and I just waited that okay, which one will be cool. And well, I was lucky. Most of the time it just doesn't make any sense, but this kind of architecture just came out quite quickly, and it works pretty well. Although I have to say that after I updated and finished all this work, I just tried also just removing the convolutional layers and then just replacing with another fully connected layer, and it just performs well. But I didn't want to put in the paper normal multi-layer perceptron-like network, because now this is the buzz, like, okay, convolutional neural networks, this is. So, but I used, especially the convolutional network increases quite a bit the computation time, but it's good, it's working. So I have this kind of neural network, I have this 98 inputs, if you remember, so I have like 48 features, doubled, now it's 96. This mean and STDF values, they are scaled between 0 and 1. And I read on the internet that, oh, this ReLU and leaky ReLU functions are the ultimate godness for neural networks. They are really, really good. So if you will use it, your network will do like miracles. And especially this came up because in some of the papers in the field, I learned that they tried deep belief nets, if I remember right, which is a kind of neural network. I think they are using batch normalization layers between after the fully connected, and they have some kind of specifics for the learning, how they are learning with this network. There is some unsupervised pre-training before you started to do the supervised learning. And I read somewhere that these are obsolete because somebody invented these leaky ReLU functions, and these are the ultimate goodness. It gives better results than the deep belief net, so just use normal neural nets with this function and it will be so powerful like the deep belief nets or better. So I'm using this leaky ReLU for all the fully connected network, and I had just a convolutional network with this kind of parameters. The convolutional filter is 9 because it worked the best. Average pooling is because it's worked the best. There is another option like the max pooling, but there is for this problem and dataset there is not too much difference. So especially I could change these parameters even to have this like 150 or this is like 50, and the same network will work almost the same good. I just use the, okay, if the first layer is 200, then the second is also 200, and why put 50 to the end? Let's divisible with 100, so it was 100. And the output layer is like 14. And I haven't used batch normalization. Maybe this is the problem of this framework, but the batch normalization layer didn't work too well, and more units didn't add more to this stuff. And things are not really important here, like what does it mean, the different colors. This is from my paper. And the thing is that these are the traditional learning methods, like random forest, naive Bayes, SVM, and blah blah blah. And this is my convolutional network. And what is important, that bigger is better. And all the time the CNN was just all the time better. So for all different colors, it's outperforming all other learning methods, and I was surprised, especially, but it does work really well. And for me, I have an AMD FX computer with 8 cores, and this CNN what I have, it scales up to 5-6 cores, and I found like 50 epochs are the best for training. After that, the training error are although decreasing, but the testing error will increase. So this 50 is not a magic. It happened that this kind of architecture for this problem, somehow the 50 is good. And as I mentioned, I have different kind of data sets like small, medium, and big. and somehow all the time the 50 worked best for epochs, like until the best performance I got from the CNN, and the prediction time is quite good on that machine, like it's very quick. Well, this is not a big network. Just compare the tiny-dnn with the for me failed network, so I'm just dropping out the convolutional bullshit and I'm just using the two fully connected layer with 200 units and with relu function because it was available in Caffe and also in this Dynet. And these frameworks, I don't know why, but these just fail. They can learn the small or the medium size data sets with the same features. Everything is the same. They can learn and everything like the gradient function, everything is exactly the same for learning the problem, but somehow they can learn the small or medium sized data sets, but for the biggest one, what I presented here, they are fail, and I'm just showing how they are failing. So this is the Dynet. Probably you don't remember. So this has also GPU acceleration, which is quite easy to enable, and especially with GPU, I can learn 10 times faster than on CPU, which is single core in this framework. But the problem is that doesn't matter how much I'm learning, how long, this is especially the same. So the training and the test error remains the same, and this is the loss function, this E especially, and it's just jumping around. It's never really decreasing. And I'm not saying that okay, I'm just tried with this and okay, this is failed so bad. I really tried everything. Tried to change the gradient function, the learning rate. I tried to change, add more layers, different activation functions. I tried many different things, but it can't learn. And I don't know why, because this is not a huge problem. It's not big data, so it should learn. It should. And the Caffe was a huge disappointment to me because it's like mainstream. Everybody says Caffe, it's good and nice, and it's failed more than the Dynet. So the loss function is completely jumping around, and it's like the accuracy is 6% instead of like 80 or 90. So it's a huge fail, and it doesn't matter how long I'm running this. If I'm changing some parameters like smaller learning rate, or I'm trying to tune it, then the accuracy can go up to 60 or something like this, but this doesn't make any sense. This should work. And all I can think of currently that these frameworks are not designed with one-dimensional data, like they are from the beginning, like images. Especially the Caffe, it can only take images like input, and I provided a patch for them to accept different kind of data than that with OpenCV. But and especially I will compile an example and I will submit like a bug to these frameworks, and they can look into more, the original developers, why it fails, because in my opinion this should really work. And I had really like with the Caffe Intel, it would be really cool if this would work with GPU acceleration, multi-core training also. It would be really nice if this would work, but unfortunately it doesn't. And why I'm pretty much in love with tiny-dnn now, because it's even in the other frameworks which can learn the smaller data sets, takes them a lot of iterations to go through until they are learning with like 90%. But the tiny-dnn, I don't know why, but it converges very, very quickly. I'm just the first epoch. The first epoch is just I'm using like batch learning, and the batch size like 64. So in one epoch, it pushes the data set only once to the network, and the tiny-dnn is already able to learn like 72% like train accuracy, and the test accuracy is also very good. And this is like 51 seconds, so it's nothing. In 1 minute I could see that, okay, well, this is really starting to work out. And after that, obviously the training doesn't go like a high rocket, but it will be like slow down like the improvements. But, and I didn't put here everything, it runs for like 1.5 hours. This shows like the estimated runtime like 40 minutes because it doesn't have the convolutional layers. But if it would have, then it would run like 1.5 hours. But this is really good. I mean, I don't understand why the other frameworks doesn't start to really converge more quickly. And that's it. Sorry to talking so much. Yeah, and I don't know, so most likely my problems are like my data is one-dimensional, so it's not image. But I also tried like maybe the Caffe is optimized to take like values between 0 and 255, like these unsigned characters. So I scaled the data to that, but it also didn't got it. And the tiny-dnn, what I favor now, it's also not like silver bullet, because one user reported that there is some data set called CFAR10, which is, I think, some kind of image data set. And the guy reports if he does some kind of pre-processing for the images, like doing it grayscale and blah, 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 then he is getting very good learning after some point, like the convolutional net can learn it from 93%, but in the next epoch the accuracy drops to 25. And well, we don't know exactly what's going on there. I didn't experience this, but at least also he reported that the training converges very quickly with the accuracy. It doesn't need 10,000s of iterations to getting some meaningful accuracy out of the network. So, yeah.
Okay, so my comments, it's really great to see these kind of failure modes when you're teaching deep learning networks, because these are what you kind of hit like 49 times out of 50. you always hit those, and people document them very scarcely, and people cannot learn from the mistakes of others and so on. People believe that it's all roses and dancing with hamsters or something. Yeah. but really, the learning rate you said was at 0.01. It seemed a bit large to me. I think typically you would use something tens or 100s of that value, so it might diverge because of that alone. And also these frameworks do have bugs. For example, TensorFlow has many bugs fixed all the time, and even this IDOF implementation of wavenets, it has well, at least one workaround there. In addition to that part which was missing GPU backend, but one workaround to kind of fix some TensorFlow bug or work around it. And I at least have many times kind of hit my head on the wall with TensorFlow when it just gives non-answers at some point. It kind of diverges to not a number, which should not happen. And I kind of I traced it to a specific version of QDNN from NVIDIA. So it was a problem with that library, and kind of using correct versions, it got over that. So it's a new field, and all these frameworks have different kinds of bugs, but the algorithm should be the same. So if you run the same architecture on different frameworks, it should you get more or less exactly the same results.
Yeah.
So there is probably some reason why that's not happening. Also, you remove the convolutional layer, it might make all the difference, because if you have only fully connected layers, then the error propagates differently. When you have convolutional layers, it kind of
but for the last slides, I'm using exactly the same without convolutional for all, and I use that to have really something simple. So nobody can say, oh well, yeah, the convolutional blah blah blah, there can be something wrong. This is like really like very easy, like just 2 layers with 200 neurons, each should work, and it doesn't. And this is like really something's most likely something is there is some characteristics with my data, because why it fails with this, because these frameworks, I'm not saying that they don't work at all, because my entering criteria was for these frameworks that do they provide the deep learning hell over this MNIST dataset, and with this LeNet or how does it called architecture law. Is there an example which can learn this dataset and give good numbers and blah blah blah? And especially for the Dynet, the LeNet, for the Dynet framework, the MNIST example using this kind of network, like 200, and 2 layers, and especially that was also one reason why I chosen this simplified, because it was very similar to my architecture, so, and it was simple. And yeah, I don't know. For the NAN values, I searched also on the internet. I could see some reports for some users that they are not getting anything out of the deep network, and it was called all the time to first check your data, because this framework somehow doesn't have any validity check for the data. So if it contains some infinite or infinity values, or how does it pronounce in English, so or NaN values, all of these will fail, and nothing checks that this is really. So I had some NaN values, and I guarded more in my stuff. Although the tiny-dnn doesn't care too much about these values, but the other frameworks really collapsed.
Yeah,
with this.
There are ways to kind of implement these things, and one thing you should always do is kind of use very small amount of data and start with simple models, and make sure you can get it overfitting your data. So then you at least know that your data is going in and the system is learning something correctly, and then you increase the complexity and so on. So it's a kind of a progressive process in any of these architectures, because there are very limited support for debugging these things, and you don't really, they're opaque. You cannot see what the system is thinking, so you kind of have to lean on your intuition how the error propagates and so on.